All right, everyone. Let's dive into something really cool today. We're talking about aerial data acquisition. Now, don't let the big words scare you. This is all about how we collect information about the Earth from the sky to create super detailed maps and models. Imagine looking down from an airplane or a drone and capturing pictures or data about the land below. That's what this is all about. It's like giving the Earth a high-tech photo shoot to help us understand it better for things like city planning, farming, or even disaster management. Let's move to the next slide to see what this process involves.
So what exactly is aerial data acquisition? It's a fancy way of saying we're collecting information about the Earth from up high, usually from 120 meters or more in the air. We use things like airplanes, drones, or even satellites to do this. Instead of walking around on the ground with a measuring tape, we use high-tech tools like cameras or laser systems called LiDAR to take pictures or scan the land. It's like taking a super zoomed-in photo from the sky without ever touching the ground. This helps us make accurate maps or 3D models for all kinds of uses. Next, let's look at the tools we use to make this happen.
Now, what is the key components of aerial data acquisition? Let's break down the two main parts of aerial data collection, the platform and the sensor. The platform is like the vehicle that carries our tools. It could be an airplane, which is great for covering huge areas, a drone, which can get super close-up shots, or a satellite, which sees the whole world but from far away. Then we have sensors. These are the gadgets that actually collect the data. Think of cameras that take pictures, or LiDAR, which uses lasers to create 3D maps of the land. It's like giving our platform a pair of super smart eyes.
Let's talk about drones, those little flying machines you might have seen buzzing around. Drones, also called UAVs or RPAS, are like remote-controlled helicopters, but way smarter. They don't need a pilot inside. They're either controlled by someone on the ground or can fly on their own using preset plans. Drones carry cool gadgets like cameras, lasers, or heat sensors, so they can do things like map land, check crops, inspect buildings, or even help during disasters. They're super versatile, cheaper than airplanes, and can reach tricky spots. It's like having a flying robot helper.
This slide seems to focus on the parts of a drone. Let's imagine we're talking about what makes a drone work. A drone has a frame that's like its skeleton, holding everything together. Then there are propellers, which are like the wings that make it fly. And of course, it takes a lot of smart engineers to design and build these drones. They make sure the drone can carry cameras or lasers and fly safely. It's like building a high-tech toy that does serious work.
Let's discuss the types of UAVs based on design. Drones come in different shapes, like cars come in different models. First, we have fixed-wing drones, which look like mini airplanes. They need a runway to take off and land, but can fly long distances, perfect for big mapping jobs. Then, multi-rotor drones. Think of those quadcopters with multiple propellers. They can hover in place, making them great for close-up photos or inspections. Lastly, hybrid drones are like the best of both worlds. They take off like a helicopter, but fly like an airplane. Each type is used for different jobs, like mapping a forest or checking a skyscraper. Next, we'll look at how they launch.
Let's talk about how drones get into the air. Fixed-wing drones need a runway, a catapult, or even a hand toss to take off, kind of like launching a paper airplane. Multi-rotor and hybrid drones, though, can lift off straight up like a helicopter. That's called VTOL, or vertical takeoff and landing. This makes them super flexible for tight spaces. Imagine launching a drone from your backyard versus needing a whole runway.
Let's see how drones are categorized next.
Categories of UAVs based on weight. Not all drones are the same size. In India, the government, through the DGCA, splits drones into categories based on weight. We have got nano drones, tiny ones under 250 grams, like a small toy. Then micro drones, up to 2 kilograms. Small, medium, and large drones go up to 150 kilograms or more. Each size has different rules, like how high they can fly or where they can go. You can check these rules on a website called Digital Sky. It's like a driver's license for drones. Bigger drones, stricter rules. Let's look at those rules next.
Flying a drone isn't just about pressing a button. There are rules to keep things safe. For example, tiny nano drones can only fly 15 meters high, about the height of a 2-story building. Bigger drones can go up to 120 meters, but need special permissions for certain areas, like near airports. All drones must fly where you can see them, and only during the day. Some need a flight plan, like telling air traffic control where you're going. It's all about keeping the skies safe, like traffic rules for cars. Next, let's talk about the gadgets drones need.
Drones need certain gear to fly safely, especially the bigger ones. For example, anything bigger than a nano drone needs an ID plate, like a car's license plate. They also need GPS to know where they are, a return to home feature in case they get lost, and even anti-collision systems to avoid crashes. Some drones have geofencing, which is like an invisible fence that stops them from flying into restricted areas. It's like giving drones a brain to stay out of trouble. Let's check out how we track these rules next.
Before flying a drone, you need to check the airspace map on the Digital Sky website. It's like Google Maps for drones, showing where you can and can't fly. The map changes, so you have to check every time. There are green zones where flying is okay, yellow zones where you need permission, and red zones where it's a no-go, like near airports. It's like checking the weather before a picnic. Let's move on to the cool gadgets drones carry.
Now, let's talk about the sensor that drones use. First, optical sensors take regular photos, like your phone camera, but they create high-res maps or 3D models. Multispectral sensors are like plant doctors. They check crop health or soil moisture. Hyperspectral sensors can tell what materials are on the ground, like spotting pollution. Thermal sensors see heat, so they're great for finding leaks in buildings or spotting wildfires. And LiDAR sensors use lasers to make super-accurate 3D maps. It's like giving drones X-ray vision.
This slide shows how different sensors see the world. An RGB is like your eyes, seeing red, green, and blue to make colorful photos. Multispectral see a few extra colors, like infrared, to check plant health. Hyperspectral see a whole rainbow of colors, helping us identify specific materials, like minerals or pollution. It's like going from a basic camera to a super-powered microscope. Optical cameras, or RGB cameras, take pictures like your smartphone, but way sharper. They create things like orthomosaic images. Think of a giant stitched-together photo of the land. They also make digital surface models, which show the height of everything, like buildings and trees. Plus, they can build 3D models of an area. Imagine seeing your neighborhood in a video game. That's what these cameras can do. Multispectral sensors are like health checkers for the Earth. They use colors like blue, green, red, and infrared to create maps that show how healthy plants are or how moist the soil is. They also make digital surface models, or DSM, and digital terrain models, or DTM, to show land height. It's like a doctor's report for crops or forests. Multispectral sensors are like health checkers for the Earth. They use colors like blue, green, red, and infrared to create maps that show how healthy plants are or how moist the soil is. They also make digital surface models, or DSM, and digital terrain models, or DTM, to show land height. It's like a doctor's report for crops or forests. Thermal sensors see heat, not light. They create heat maps to show where things are hot or cold. For example, they can spot a leaking pipe in a building or find a wildfire in a forest. They're also great for checking if a house is losing energy. It's like having heat vision goggles on a drone.
Now discuss about methodologies adopted for aerial data acquisition in NAKSHA. For NAKSHA, we use three main ways to collect data: nadir imaging, where the camera points straight down; oblique imaging, where it's tilted at an angle; and combined oblique plus LiDAR, which mixes angled photos with laser scanning. Each method has its strengths, like mapping flat land or creating detailed 3D models. It's like choosing the right tool for the job. Let's break these down one by one.
Nadir imagery is when a drone's camera points straight down at the ground, like looking down from a ladder. This gives you a clear, top-down view with no distortion, perfect for making flat maps or measuring distances accurately. It's great for things like mapping farmland or roads because it covers big areas with clear details. It's like taking a perfect overhead photo.
Oblique imagery is different. It's like taking a photo at an angle, say 40 or 50 degrees. This lets you see the sides of buildings or hills, not just the top. It's super useful for things like city planning or inspecting structures because you get a more 3D view. Imagine taking a selfie from an angle to show more of your face. That's what oblique does for the land. Next, we'll combine this with LiDAR. Now, this is where it gets really high-tech. The combined oblique plus LiDAR system uses angled cameras and laser scanning together. The cameras take detailed pictures, while LiDAR shoots lasers to measure exact distances, creating super accurate 3D maps. This is perfect for tough areas like dense forests or hilly terrain where regular photos might miss details. It's like combining a photo album with a measuring tape.
Now we discuss about overview of LiDAR technology. LiDAR stands for Light Detection and Ranging, and it's like a laser-powered measuring tool. It shoots out laser beams, measures how long they take to bounce back, and creates a super detailed 3D map of the ground. It's amazing because it can see through trees or work at night, unlike regular cameras. It's used for things like mapping roads, forests, or even disaster areas. Think of it as a drone with a laser ruler that measures everything precisely.
LiDAR systems have three main parts: a laser scanner that sends out laser pulses, a GPS to know exactly where the drone is, and an IMU that's a fancy gadget that tracks the drone's movements. Together, they create a super accurate picture of the land below. It's like a high-tech surveyor flying in the sky, measuring every hill and valley perfectly.
There are three types of LiDAR. Terrestrial LiDAR sits on the ground and is great for mapping buildings or bridges. Aerial LiDAR flies on drones or planes and maps huge areas like forests or cities. Bathymetric LiDAR uses special green lasers to map underwater, like rivers or coastlines. Each one's like a different tool for a different job: ground, air, or water. Raw LiDAR data is like a big cloud of points. Each point is a laser measurement of the ground. It's not pretty yet, just a bunch of numbers about height and distance. But with some computer magic, these points turn into detailed maps or 3D models.
Think of it like a sketch that gets colored in later to make a beautiful picture. Once we process LiDAR data, it turns into cool stuff like digital elevation models, maps showing the height of the ground, or point clouds, which are like 3D dots you can spin around on a computer. You can also make contour maps, like those squiggly lines on hiking maps showing hills. It's like turning a bunch of numbers into a 3D world.
Let's compare our three methods. Nadir gives a straight-down view, great for flat maps like farms or roads. Oblique shows angles, perfect for 3D models of buildings or cities. Oblique plus LiDAR combines both, giving you detailed pictures and laser-accurate heights for things like rugged terrain. Each one's like a different camera lens for different jobs.
This slide shows the steps to create maps and 3D models. Let me explain the process simply. First, we fly drones to collect images and data. Then, we stitch the images together and process the data with computers. This creates things like flat maps or 3D models you can explore on a screen. It's like taking a bunch of puzzle pieces and putting them together to make a picture of the land.
Let's see what kind of data we use. To make these maps and models, we use two kinds of data: 2D imagery, like photos from cameras, and 3D elevation data, like measurements from LiDAR. Together, they create a complete picture of the land, how it looks, and how high it is. It's like combining a photo with a ruler to get the full story. Let's look at an example of an oblique camera's work. An oblique camera takes angled photos that show the sides of things, like buildings or hills. The result is a detailed picture that's almost like a 3D movie. You can see more than just the top. This is super useful for planning cities or inspecting structures. It's like looking at a house from the street instead of just the roof. Next, we'll talk about processed data. Once we collect all this data, photos, laser measurements, it goes into a computer to be processed. This means cleaning it up, combining it, and turning it into something useful, like a map or 3D model. It's like editing a raw video to make it look polished and professional. Let's see one of the results: orthorectified images. Now, what is orthorectified image? An orthorectified image is a super accurate photo from above that's been fixed so distances on the image match real-world distances. It's like a perfect map you can measure with a ruler. These are used in things like GPS systems or city planning because they're so precise. Imagine a Google Maps image you could measure like a blueprint. These slides show examples of true orthorectified images from Nadir cameras. These are top-down photos that are super accurate, like a perfect bird's-eye view. They're used for things like planning roads or measuring land for farms. It's like having a giant, perfect photo of the ground you can trust completely.
Now, let's talk about elevation models, which show the height of the land. A digital surface model, DSM, shows everything: trees, buildings, the works. A digital elevation model, DEM, shows just the bare ground, no trees or buildings. A digital terrain model, DTM, is like a DEM, but with extra details, like rivers or ridges. These are used for things like planning roads, studying floods, or building cities. It's like a 3D map of the Earth's shape.
This slide compares DSM and DTM/DEM. A DSM includes buildings and trees, while a DEM or DTM shows just the ground, maybe with rivers or hills added. Think of a DSM as a photo of a city, and a DEM as a photo of the empty land underneath. These help with things like flood planning or construction planning. Processed LiDAR data turns those raw laser points into useful stuff like 3D maps or elevation models.
It's like taking a pile of measurements and turning them into a detailed picture of the land. This is used for everything from building roads to studying forests. It's like sculpting the earth on a computer.
Let's talk about 3D reality models. A 3D reality model is like a virtual version of the real world. Using photos and LiDAR, we create a 3D model you can explore on a computer, like a video game of a real place. These are used for city planning, architecture, or even virtual tours. Imagine walking through your city on a screen. That's a 3D reality model.
Here's an example, a 3D reality model of a part of Delhi. This model shows buildings, roads, and terrain in 3D, like a digital dollhouse of the city.
A 3D vector model is another way to show the world in 3D, using lines and shapes to represent things like buildings or roads. It's less like a photo and more like a clean digital drawing. These are great for engineers or planners who need clear, simple designs.
This was all about aerial data acquisition. Hope you found it useful. Thank you.